Let's continue in this video. So I'm going to build up on the program that we wrote last time. I'm just going to do a little bit of cleaning here, remove these comments. And in this video, what I'm going to show you is now that you know how to declare space for a byte or a word and how to declare space for multiple bytes and words in memory, I'm going to show you the equivalent of C in assembly. So if you write a statement in C to declare an integer or an array of integers, how does that actually get translated into assembly instruction? So let's take an example here. So let's say I would like to declare uh, integer x equals to 5, for example. This is my C language instructions or code, right? Let's say we also want a character. So a character, we can call this Z equals to A. And let's say we would like to do an integer array. So in this case, x, z, or you can call it like x again. So if I have this, and let's do a static character array. Let's call it this. This will be, let's say, A, B, and C, right? So this is a typical code that you would see in C programming. Now let's translate this into assembly instructions. So if I want to declare space for an integer will be basically translated into a word. An integer will take 4 bytes in memory. And which of these two will allow me to have 4 bytes? It is the word. So the equivalent of the first statement in C is going to translate to um, int, or in this case, dot word. And I'm going to call this x, but I can't do this here, so I actually have to put it as a label, right? So word, and the value of that is 5, and I just put 5. That's it. And if I want to do a character occupies 1 byte in memory, and which of these directives will give me a byte? That is the dot byte. So here I'm going to have z. Let's give this, that's a byte. And what is the value of that byte? That's capital A. Next, I have an array of integers, and the name of that is also x. Maybe we should just call it something else. Let's call this x ARY for an x array. So here it's x ARY, and I'll move these one more tab. So this is a character array, which means an integer array, sorry. So again, I need to use the word directive because that will give me 4 bytes for each value. And I can separate them by comma. So this is 1, comma 2, 3, and 4. And finally, I have a character array called CHARY. So since this is a character array, again, I need to use a byte. And for this one, I can declare the characters as A, B, C, like that. And I'm done. So these are the equivalent values or the equivalent instructions in assembly. Now you may ask yourself, is there a different way of doing the character array The answer is yes, you can do that. You can actually use the ASCII directive instead, so you can do an alternative way to do the character array is to use the ASCII and do A, B, C. Now, if I want to access these values, I need to use a pointer that will point to their address. So I'm going to use something similar to what I had before in my loop. So let's change this a little bit and load the register R0 with the address of X. I'm going to load R1, register R1 with the address of Z. I'm going to load register R2 with the XARY, or the address of that uh, array, and then R3 with uh, character array, and LDR R4 with, well, now I have two character arrays, so I'm going to just call this 2, like that. And I'm going to show you how those instructions are actually loading the address of these variables or arrays into the registers that used in the instruction. Okay, so let's go to memory and inspect what we have here. So if I open the memory tab, let me put it here. So I have these values, 5A, 1, 2, 3, 4, A, B, C, and then an ASCII A, B, C. Let me just make some space to look at the memory. Then maybe see the ASCII equivalent of that. And even for this, I'm going to see one word per line, simply because it's easier to view it this way, so you guys can see the instructions. If I make this full screen, the resolution will be bad and you can't really read the text in the video. Okay, if I look at the memory content, this is from before. This is my 22D 5N0C. This was my byte array right here, followed by the word 2391, which is 957 hex, and so on. And then I have 1, 2. This is 1 occupying one word, 2 occupying one word, and then I have 5, which is this 5 right here. And then I have a byte that is A. So A in hex, if you look at the ASCII table, A is 41 hex. Let me pull that up. So if you look at an ASCII table, you will see that capital A right here is 41 in hex. And you can refresh your memory with what these letters values are in hex. Maybe we can talk about it in a different video. But you need to know that capital A is 41, lowercase a is 61, and then they go one at a time. So capital B is 42, capital C is 43, and so on. Lowercase b is 62, lowercase c is 63, and so on. And the value, the character 0, is 30 hex, and 1 is 31, 2 is 32, and so on. So it's always a good practice to at least remember capital A, lowercase a, and the value 0. From there, you can add, knowing the alphabet, you can add, if I want to know what is K, well, K comes after A. I can A, B, C, D, E, F, G, H, I, J, K, and then I go from 41 until I hit for B. And similarly, if I want to calculate, what is the hex value of 4 in ASCII, I start with 30, and then 4 after that is 34, so that's 34 hex, and the same thing with A. So knowing capital case A, lowercase a, and 0 usually help you figure out the value for whatever you have in your memory in terms of ASCII ASCII values. So let's go back to the program. So that is my 41 right here. So A is 41, this is my byte, and since this is occupying only one byte, I have 41 right here, followed by a word. This word is 1. So you will see that this one starts right here, and it will occupy a complete word. So it will occupy 4 bytes. So this is 1, 2, 3, 4. So all these bytes are occupied by the first array value of 1 in memory, followed by 2, 3, and 4. So this is my 2, and it's going to follow the same principle. This is my 2, and it's occupying 4 bytes. So this is the first byte, second byte, third byte, and this is the fourth byte, followed by 3, the first byte, second byte, third byte, and the fourth byte, and then followed by 4, and so on. After that, I have my byte array, character array of ABC. So you will see here that A, lowercase a, is 61, B is 62, C is 63, and you will see that this character array and the ASCII have the same content in memory, right? So this is 61, 62, 63, and the next one is 61, 62, 62, and 63. Okay. Perhaps we can talk a little bit about the memory address and how I'm calculating the bytes and all that for a little bit. I did mention extensively how this is working in another video when we set up the Intel FPGA monitor program, how these addresses are going up by 4 and whatnot. But I will maybe spend a few more minutes in the next lecture to describe how the addressing is working and like how you have 1 byte per address and how we're actually navigating through this. But for now, what I would like to do is I would like to go through these instructions, and I'm going to show you how these registers are going to contain the address, not the data, of the character or the integer, but the address of the integer or the address of the array. This is very important because this really makes a lot of sense if you go from here to higher level programming. It will give you a lot of understanding of why, for instance, a pointer to an array is basically a pointer to the first element in the array. So let me step through this instruction. So the first one that got executed is loading register R0 with the address of X. So if I pull my register, let me keep it here. So register R0 contains the value of 54, and if I go down to 54, this is 54 right here, this is address 54, which is basically where my 5 is stored, and this is my word right here. This word is located at address 54 hex. If I execute the next instruction, I'm going to load the address of Z into R1, and the address of Z is going to be 58. Well, it's 4 plus 54, so that's 58. So right here. So the address of that character, of that byte A, is at address 58, which is right here, and that is the address right here. Now 58 is in R1. Now if I load the address of the X array into R2, I get the value of 59 because Z was one byte, right? Z is 1 byte. So obviously, what comes after 58? 59. So R2 contains 59. If I go to 59, this is 58 right here. Now this is 59. Okay, and as I've shown you in the previous video, you can actually make a small loop and you can step through it and increment by 1. But now what you see is that when you point to any label in your assembly, you're essentially pointing to the address of the first element in your label. You're pointing to the address of the first element in your label. In the next video, I'm going to show you how these addresses and the memory content are related and how I'm reading those values, and how, like, for instance, like this 41 is essentially sitting at address 58, and how we're going from 58 to 5C. But for now, I wanted to show you, some more on space allocation directives using word, byte, and an ASCII. And I wanted to show you that you can point to these using the labels that you provided. I wanted to show you how a C language code can be translated into assembly equivalent instructions, and that you can actually point to the address of these labels, which are essentially the address of the variables that you're going to use. Thank you for watching, and I'll see you next video.